Look up at the night sky, and the universe appears vast beyond comprehension, a scattered tapestry of stars and galaxies stretching into darkness. Yet beneath this display of light lies a deeper and far more subtle question. Does the universe have a shape? At first, the idea seems strange. Shape is something we associate with objects, with boundaries, surfaces, and edges, but the universe is not an object within space. It is space itself. And understanding its form requires us to abandon everyday. For the shape of the universe determines how it moves, how it expands, and how it will ultimately end. Whether it will continue to grow forever, slow, and stabilize, or one day collapse back upon itself, is written into its geometry. We cannot step outside the universe to examine it. Instead, we must infer its shape from the way light travels, from the distribution of galaxies, and from faint echoes left over from the universe's earliest moments. To understand the universe, we must first understand a form without edges, yet rich with structure governing everything within it. If you were to stand on the edge of a cliff overlooking a vast ocean, your eyes would be drawn to the waves. You would watch the water crashing against the rocks, the white spray flying into the air, the rhythmic, hypnotic motion of the tides. You would see the water as a thing, a substance with weight, with power, with a tangible reality. But if you were to look up, away from the water and into the clear blue sky, your intuition would tell you a different story. You would see the birds, the clouds, perhaps the sun, but the space between them, to our eyes, that is simply emptiness. It is the absence of things. It is merely the gap that separates one object from another. This is the great illusion of our daily lives. We move through the world perceiving space as nothing more than a container, a passive, silent, invisible box in which the drama of the universe plays out. We imagine that if we were to take the universe and remove every star, every planet, every atom of gas, and every photon of light, we would be left with a pure static void, a stage that has been cleared of its actors, waiting in eternal silence, unchanged and unchangeable. For centuries, this is exactly how science viewed the cosmos. Isaac Newton, the giant of classical physics, described space as an absolute framework. To him, space was rigid, eternal, and immovable, was the scaffolding of reality, a fixed grid against which the motion of planets and falling apples could be measured. In this view, space did not participate in the events of the universe. It merely held them. It was indifferent. A star could explode, a black hole could form, or a galaxy could collide with another, and space itself would remain aloof, a silent witness that felt nothing and changed for no one. But this view is wrong. To understand the shape of the universe, we must undergo a profound shift in perspective. We must dismantle the idea of space as a void and replace it with something far more strange and far more beautiful. We must begin to see space not as a stage, but as an act. Space is a thing. It is a physical entity with properties, with behaviors, and with a hidden structure. It is not a passive emptiness, but a dynamic, flexible fabric that weaves the cosmos together. It is a substance that can stretch, that can twist, that can tremble, and crucially, that can curve. Imagine for a moment that you are a deep-sea diver, submerged in the clearest waters of the Pacific. If the water is perfectly still and clear, and you are floating far from the bottom, you might forget that the water is there at all. You might feel as though you are floating in a void. But the moment a current sweeps you sideways or a pressure wave pushes against your chest, you realize that the emptiness around you is actually a medium. It has density, it has flow, it creates friction and resistance, it carries sound and force. As space is the ocean in which the stars, it is the medium that connects us to the most distant galaxies. And just like the ocean, it is not the same everywhere. It has a geometry, it has a texture. When we speak of the fabric of space, we are using a metaphor, but it is a metaphor that points to a literal physical truth. In the language of physics, we call this the metric field. It is the set of rules that defines distance and direction at every point in the universe. In our everyday experience, these rules seem fixed. If you take two parallel lines, say two beams of laser light, and shoot them forward, you expect them to remain parallel forever. You expect the angles of a triangle to always add up to 180. This is the geometry of the flat, rigid box. It is the geometry we learn in school, sketched on sheets of paper. But space is not a sheet of paper. It is more like a sheet of rubber. It is a material that creates the very definitions of straight and distance, and those definitions can change. Think of the universe as a vast, invisible tapestry. If you pull on one corner of a tapestry, the threads distort across the entire surface. The pattern shifts. The straight lines become curved arcs. The distance between 2 points on the fabric changes, not because the points have moved, but because the fabric itself has stretched. This is the reality of the cosmos. Space is malleable. It is constantly responding to the presence of matter and energy. It is constantly fluctuating. It is capable of expansion, stretching the distance between galaxies so that they rush away from one another, not by moving through space, but by the swelling of space between them. Consider the expansion of the universe. We often say that galaxies are flying apart, but this conjures an image of shrapnel flying from an explosion into a pre-existing room. That is not what is happening. The room itself is growing. The fabric is stretching. If space were truly a nothingness, a simple void, it could not expand. How can nothing get bigger? Nothing has no size. Nothing has no boundaries, but space does expand. We can measure the rate at which it stretches. We can time the light as it traverses this growing medium. The simple fact that the universe is getting bigger is the most potent evidence we have that space is a physical reality. It is a substance that can be created, pulled, and distorted. This flexibility changes everything. It means that the universe is not a rigid grid of X, Y, and Z coordinates that have existed forever. It means the universe is a fluid geometry. Imagine an ant walking across a giant trampoline. If the trampoline is tight and unoccupied, the ant can walk in a straight line from one side to the other. The space of the trampoline is flat, but if you stand in the middle of the trampoline, your weight depresses the fabric. You create a valley, a curve in the surface. Now the ant trying to walk in a straight line finds its path bent by the shape of the surface itself. It dips down into the valley and climbs back out. To the ant looking only at the rubber beneath its feet, it feels a force pulling it toward you. But from a distance, we see the truth. The ant is simply following the curvature of the world it lives on. This is the essence of the new geometry. We are all planets, stars, humans, atoms crawling along the surface of a four-dimensional fabric that is warped and twisted by the energy contained within it. We are not falling through a void. We are sliding down the geometric slopes of space itself. But this fabric is not merely a responsive surface, it is a repository of energy. Even if we were to remove all the stars and galaxies, modern physics tells us that the vacuum of space would still be vibrating with potential. It seethes with virtual particles, appearing and vanishing in fleeting moments, a quantum foam that underpins reality. This suggests that the fabric is woven from the fundamental fields of nature. It is thick with activity. To understand the shape of the universe, we must first embrace this tangibility. We must stop looking at the dark patches of the night sky as empty. We must start looking at them as structure. When we look at a distant star, the light that reaches our eyes has traveled for billions of years across this fabric. It has not traveled in a straight line because there are no truly straight lines in a curved universe. It has followed the contours of space, dipping around galaxies, stretching as the universe expands, rippling as gravitational waves pass through it. The light is a traveler on a winding road, and by studying the path it took, we can map the road itself. This is a concept that defies our primate brains. We evolved to understand objects that we can hold in our hands: rocks, sticks, fruits. We understand geometry as the shape of a solid thing. A sphere is a ball. A cube is a box. But the geometry of the universe is the geometry of the inside. We are trapped within the object we are trying to measure. We are like silkworms inside a cocoon, trying to understand the shape of the silk by crawling along the threads. We cannot step outside the universe to look at it. There is no outside. If space is the fabric of reality, there is no place where the fabric is not. The shape of the universe is intrinsic. It is defined by the relationships between points within the universe. So when we ask, does the universe have a shape? We are asking about the weave of this fabric on the grandest possible scale. Is the fabric pulled tight and flat, extending forever in all directions? Is it curled up like a sphere so that if you traveled far enough in one direction, you would eventually return to where you started? Or is it flared out like a saddle, curving away from itself in an infinite deepening divergence? These are not philosophical musings. These are questions about the physical properties of the medium we live in. Just as a sound wave travels differently through water than it does through air, the history of the universe, how it began, how it evolved, and how it will end, depends entirely on the tension and the curvature of space itself. If the fabric is too curved, the universe might one day snap back, collapsing in a catastrophic big crunch. If the fabric is shaped differently, it might stretch so thin that eventually every atom is torn apart in a big rip. The geometry is the destiny. So, as we embark on this journey to map the cosmos, remember, we are not mapping the arrangement of the furniture, we are mapping the shape of the room. We are exploring a dynamic, living geometry that connects every point in time and space. We are trying to visualize the invisible currents of the ocean in which we drew. This realization that space is a thing, that it is flexible, that it is the primary constituent of the universe, is the gateway to understanding everything else. It is the first step in seeing the universe not as a collection of isolated islands, but as a single, cohesive, and beautifully curved whole. This fabric is subtle on the scale of our daily lives. Space appears rigid and flat. A carpenter does not need to worry about the curvature of the universe when building a table. The angles of his square remain true, but this is only because the Earth is small and our local gravity is weak. We live in a quiet, flat backwater of the cosmic ocean. But zoom out. Zoom out past the solar system, past the Milky Way, to the scales where clusters of galaxies drift like dust motes. Here, the true nature of space reveals itself. Here, the fabric is twisted into great knots and valleys. Here, the geometry dominates, and it is here, in the grand sweeping curves of the cosmos, that we find the answers to our existence. For if space can curve, it can do things that nothingness never could. It can carry vibrations. It can trap light. It can expand faster than the speed of light. It can essentially create horizons beyond which we can never see. We are about to look closely at what causes this fabric to bend. We have established that it is a flexible sheet, a responsive medium. But what is the hand that presses down upon it? What is the force that grabs the threads of the cosmos and pulls them tight? The answer lies in the relationship between the stage and the actors. The fabric of space dictates how matter moves, but matter, in turn, dictates how the fabric curves. It is a cosmic dance, a continuous feedback loop between the container and the contained. As we move deeper into this exploration, we will see that the emptiness is the most substantial thing of all. It is the canvas of creation, and it is far from blank. It is wrinkled, it is stretching, and it is alive with the geometry of gravity. To understand the stars, we must ignore them for a moment and focus on the darkness between them. For in that darkness lies the shape of reality itself. For over 2 centuries, the Western scientific mind rested comfortably on a foundation built by Isaac Newton. It was a solid, dependable foundation. In Newton's universe, gravity was a force, a mysterious, invisible tether that connected objects across the void. The sun, massive and golden, reached out across 93 million miles of emptiness to grip the Earth, holding it in orbit like a child spinning a stone on a string. In it, the mathematics were precise. You could navigate ships by the stars and predict the return of comets using Newton's laws. But there was a ghost in the machine, a silence where an explanation should have been. Newton himself was deeply troubled by it. He could describe how gravity worked, the strength of the pull, the mathematics of the orbit. But he could not tell you why. How could a star reach across a vacuum? How could the Earth know where the sun was? By what mechanism did this force travel instantaneously through the nothingness? It was, in Newton's own words, an absurdity that no non with a competent faculty for thinking could ever fall into. And yet, for 200 years, we accepted the absurdity because the equations worked. Then came the year 1915, and a patent clerk in Berlin who dared to rewrite the rules of reality. Albert Einstein looked at the invisible tether of gravity and decided it did not exist. He looked at the rigid, static stage of Newtonian space and decided it was an illusion. Einstein's insight was not merely a correction, it was a demolition of our entire understanding of the cosmos. He proposed something so radical that it initially baffled the greatest minds of his generation. Gravity is not a force. Gravity is a shape. To understand this, we must return to our flexible fabric. We have established that space is a medium, a thing that can stretch. Einstein realized that this fabric is not separate from the objects within it. They are intimately linked in a relationship of cause and effect. He proposed that the presence of matter, a planet, a star, a galaxy, does not simply sit in space. It weighs down upon it. It distorts the geometry around it. Think of a mattress, a pristine, flat mattress. If you roll a marble across it, the marble travels in a perfectly straight line. But if you place a heavy bowling ball in the center of that mattress, The surface sinks. It curves. A depression forms, a smooth, sloping valley leading down toward the heavy weight. Now, if you roll that marble again, it no longer travels in a straight line. As it approaches the depression, its path bends. If you roll it at just the right speed and angle, it won't fall into the bowling ball, nor will it fly off the edge. It will circle around the rim of the depression. It will orbit. To an observer looking down from above, unaware of the curvature of the mattress, it would look as though the bowling ball is pulling the marble with an invisible string. It would look like a force, but there is no string. The marble is simply following the natural curve of the surface. It is trying to move in a straight line, but the straightness of the space itself has been warped. This is the heart of general relativity. Massive objects cause the fabric of space to curve, and that curvature dictates how other objects move. The Earth is not being pulled by the sun. The Earth is falling. It is rolling freely along a cosmic slope created by the sun's immense mass. We are trapped in a gravitational valley, circling the drain, saved from falling in only by our own lateral momentum. But Einstein went further. He realized that space alone was not enough to describe this. The universe is not a three-dimensional painting. It is a four-dimensional movie. You cannot separate the place where something happens from the time when it happens. Space and time are woven together into a single seamless entity. Space-time. This is crucial because gravity does not just bend space, it bends time. Near a massive object, time slows down. Deep in the gravity well of the Earth, a clock ticks infinitesimally slower than a clock floating in deep space. The curvature that we feel as gravity is actually the curvature of this combined space-time fabric. When you drop a cup from your hand and it shatters on the floor, you perceive a force pulling it down. But Einstein would say the cup is merely following the path of greatest proper time. It is sliding down a groove in the temporal dimension. The force of gravity is an illusion created by our movement through a curved four-dimensional environment. This insight, that matter shapes geometry, transforms our question about the shape of the universe. It means the shape is not a static background. It is a dynamic landscape. It is mountainous. Every star is a peak, or rather a deep valley in the fabric. Every black hole is a bottomless abyss, a puncture where the fabric has been stretched to its breaking point. Every galaxy is a vast collective depression, a bowl in the fabric of space-time, holding billions of stars together, not by glue, but by geometry. And this geometry is stiff. The fabric of space-time is not flimsy like the rubber of a balloon. It is incredibly rigid. It takes a staggering amount of mass to create even a modest curve. Consider the Earth. It is a rock 6,000 kilometers deep, weighing 6 extillion tons. That immense mass is required just to create enough curvature to keep our feet on the ground and the moon in the sky, to bend space significantly, to create the deep wells that trap light, or the grand curves that define the cosmos. You need the mass of suns, of clusters, of entire universes. This leads us to the most famous equation in history, a small piece of algebra that acts as the conversion rate for this geometry, is equal to mc Caffaire. Energy equals mass times the speed of light squared. We usually interpret this equation to mean that mass can be turned into energy, as in a nuclear bomb, or energy into mass. But in the context of geometry, it means something even more profound. Mass and energy are the same thing to the universe. Space-time does not care if an object is made of rock, gas, or pure light. It only cares about the energy density. A sufficiently concentrated beam of light would have its own gravity. It would curve space just as a planet does. This is why Einstein's insight is often summarized in the elegant phrase coined by physicist John Wheeler: space-time tells matter how to move, matter tells space-time how to curve. It is a handshake, a continuous dialogue. As the Earth moves around the Sun, the curvature of space guides it, but the Earth itself has mass. So, as it moves, it drags its own tiny dimple of curvature with it, rippling the fabric as it goes. The shape of the universe is constantly evolving, constantly responding to the dance of the energy within it. So, when we zoom out to the largest scales, we are no longer looking for a box. We are looking for the sum total of all this curvature. If you add up all the mass in the universe, every star, every cloud of gas, every photon of light, and every distinct particle of dark matter, does it create enough curvature to wrap the universe back on itself? Einstein realized that the overall density of the universe determines its overall shape. Imagine the rubber sheet again. If you place enough weights on it, the entire sheet will sag. If you place weights everywhere, evenly distributed, the entire fabric creates a global curvature. This is the transition from local gravity to cosmic geometry. Local gravity is the bump and dip of a star. Cosmic geometry is the shape of the whole sheet. If there is a lot of mass, the sheet might curl up into a ball. If there is very little mass, the sheet might stay flat or flare out. Einstein's equations provided the toolkit to measure this. He gave us the metric tensor, a mathematical machine that takes the energy content of a region and spits out the shape of the space. Before Einstein, the question, does the universe have a shape, was poetry. After Einstein, it was physics. It became a question of measurement. If we can weigh the universe, if we can determine the density of the energy within it, we can calculate the curvature. But this new view of space as a curved fabric creates new conceptual challenges. We are used to curved lines on flat surfaces. A road curves on a map. A rainbow curves in the sky. But how do you visualize space itself curving? We must rely on analogies, but we must also be careful with them. The rubber sheet analogy has a flaw. It shows the sheet curving downward into a third dimension. But the universe doesn't curve into anything. There is no underneath for space to dip into. The curvature is intrinsic. It is built into the measurements of distance itself. Think of an airplane flying from New York to London. On a flat map, the straight line goes directly east across the Atlantic. But pilots don't fly that way. They fly in a curve, arching up toward Greenland and then coming back down. Why? Because the Earth is a sphere. The straightest line on a curved surface is a curve. We call this a geodesic. In the curved universe of general relativity, light rays are the airplanes. Light always takes the quickest path. In flat space, that's a straight line, but in the presence of mass, straight becomes curved. If you were to shine a laser beam past the sun, the beam would bend, not because the light is heavy, but because the space it is traveling through is warped. The straight path wraps around the star. This was the prediction that made Einstein a celebrity. He claimed that during a solar eclipse, we would be able to see stars that should be hidden behind the sun because the sun's gravity would bend their light around the edge, bringing them into view. When this was confirmed in 1919, it proved that we do not live in Newton's rigid box. We live in Einstein's funhouse mirror. This curvature is real, it is measurable, and it is the key to the ultimate fate of the cosmos. Because space-time is a physical thing that responds to energy, It can do things that a static void cannot. It can expand, it can contract, it can ripple. When two black holes collide, they don't just bang together, they strike the drum of space-time. They send out ripples, gravitational waves, that stretch and squeeze the universe as they pass. These waves travel across the cosmos for billions of years, passing through the Earth, stretching you and me by a distance smaller than the nucleus of an atom. The fact that we can detect these waves today is the final thunderous proof that Einstein was right. Space is a participant. It acts, and it is acted upon. So, as we stand on our little planet looking up, we must shift our mental model. We are not looking into an empty room. We are looking into a gel, a fluid, a fabric that is stressed and strained by the grand architecture of the galaxies. The shape of the universe is not a static container. It is a frozen struggle between the expansion that drives galaxies apart and the gravity that tries to pull them together. The geometry is the scorecard of this struggle. Einstein showed us that the shape of the universe is not just a philosophical curiosity, it is the operating system of reality. Every orbit, every falling apple, every ray of starlight, and the very flow of time itself is dictated by the curvature of the world we inhabit. Now that we understand that the cosmos is a flexible, curved structure shaped by mass, we must ask, what does this curvature look like on the grandest scale? Is the universe curved like a ball? Is it flat like a sheet? Or is it something else entirely? To answer this, we need to understand the three fundamental flavors of cosmic geometry. We need to explore the difference between a universe that closes on itself and one that opens forever. We need to learn the language of positive, negative, and flat. We have accepted that space is a fabric, and we have accepted that mass and energy cause this fabric to curve. But when we zoom out from the local valleys of stars and planets and look at the universe as a whole, what is the overall pattern of that curvature? If the universe were a piece of origami paper, how is it folded? Cosmologists have determined that on the grandest scales, the curvature of the universe must fall into one of three distinct categories. These are not merely shapes, they are destiny. They are the three possible blueprints for reality, each with its own specific rules of geometry and its own specific end for the cosmos. We call them positive, negative, and flat. To understand them, we must perform a mental exercise. We must imagine that we are two-dimensional beings living on the surface of a giant object, unable to see up or down, only forward, backward, left, and right. The closed universe, positive curvature. Imagine first that our two-dimensional universe is the surface of a giant sphere, a beach ball or a globe. This is a world of positive curvature. On a sphere, the rules of high school geometry begin to break down in strange and wonderful ways. Think about parallel lines. On a flat sheet of paper, two parallel lines, like the tracks of a railway, will stay the same distance apart forever. They never meet. But on the surface of a sphere, this is not true. Start at the equator of the Earth. Imagine two explorers standing a few hundred kilometers apart, both facing strictly north. They are parallel. They begin to walk. As they travel northward, they both move in straight lines along the surface. Yet as they approach the North Pole, they get closer and closer together. Finally, at the pole itself, they collide. They did not turn. They did not steer toward each other. They followed perfectly straight paths, geodesics on a curved surface, and the geometry of that surface force them to converge. In a universe with positive curvature, space itself wraps around. It is a closed universe. This has a mind-bending implication. A closed universe is finite, but it has no. If you were to get in a spaceship in a positively curved universe and fly in a straight line for long enough, you would never hit a wall. You would never find the end of the universe. Instead, eventually, after billions of years, you would arrive back at the place where you started. You would approach Earth from the opposite direction. In this universe, if you had a telescope powerful enough, you could look straight ahead and see the back of your own head. A universe with positive curvature is a cozy, self-contained cosmos. It has a finite volume, even though it has no boundaries, and crucially, a closed universe is one where gravity is the dominant winner. It suggests a universe with so much mass, so much density, that the mutual gravity of all the galaxies pulls space-time back onto itself. This shape dictates a specific fate. If the universe is closed, the expansion we see today, eventually, the immense gravity that curves the space will slow the expansion, stop it, and reverse it. The galaxies will stop rushing apart and start rushing together. The universe will shrink, heating up as it compresses until all matter and energy collide in a final, fiery big crash. The reverse of the Big Bang, the open universe, negative curvature. Now imagine a different shape. Instead of a sphere, imagine the shape of a saddle or Pringles potato chip. This is a surface that curves up in one direction and down in the other. This is a world of negative curvature. Geometry here is the mirror image of the sphere. Start our two explorers again. They stand next to each other, facing the same direction, parallel. They begin to walk on the saddle. The surface curves away from itself. As they walk forward, the space between them stretches. Without turning, they drift further and further apart. They diverge. In a universe with negative curvature, parallel lines peel away from one another. The angles of a triangle add up to less than 8. This is an open universe. Unlike the sphere, the saddle doesn't wrap around. It extends infinitely. It goes on forever, in all directions, never meeting, never closing. It is infinite in volume and infinite in extent. An open universe is a lonely place. It implies that the density of matter is low, too low for gravity to ever halt the expansion. In this geometric destiny, the universe will expand forever. The galaxies will drift apart until they are out of sight. The stars will burn out, and the cosmos will grow dark, cold, and empty. This is the big free, the flat universe, zero curvature. Finally, we arrive at the third option, the one that seems most familiar, yet is statistically the most unlikely, flat curvature. This is the geometry of the tabletop, the sheet of paper, the grid. It is the geometry of Euclid. Here, parallel lines remain parallel forever. They never meet, and they never diverge. The angles of a triangle add up to exactly 180 degrees. If you launch a spaceship in a straight line, it travels forever, never returning, never curving. Like the open universe, a flat universe is infinite. It has no edge. It extends endlessly. But flat in astrophysics does not mean two-dimensional like a pancake. It means uncurved in the 3 spatial dimensions. It means that X, Y, and Z form a perfect, rigid grid that is expanding but not warping on the largest scales. A flat universe represents a cosmic knife edge. It corresponds to a very specific critical density of matter and energy. It is the Goldilocks zone. If there is just one atom more per cubic meter, gravity wins and the universe curves positively and collapses. If there is just one atom less, the expansion wins and the universe curves negatively and flies apart too fast. But in a flat universe, the momentum of the expansion and the pull of gravity are perfectly balanced. The universe will expand forever, but the rate of expansion will slow down, approaching zero, but never quite stopping. So, which one is it? We are living inside one of these three shapes right now. The light from distant galaxies is traveling along the lines of this geometry. If the universe is a sphere, the distant galaxies should look larger than they really are, because the light rays are converging like a magnifying glass. If the universe is a saddle, the distant galaxies should look smaller, because the light rays are spreading out. If the universe is flat, they should look exactly the size that standard geometry predicts. For decades, this was the holy grail of cosmology. Philosophers and theologians argued over the implications. A closed universe felt finite, cyclical, perhaps more comforting. A universe with a life cycle, an open universe felt desolate, infinite, and entropic. But nature does not care about our comfort. It cares about the numbers. The shape of the universe is not a choice. It is a measurement. To measure it, we cannot simply use a ruler. We are too small. We need a triangle that spans the cosmos. We need to look at the oldest light in the universe, the cosmic microwave background, and measure the size of the fluctuations within it. We will discuss exactly how we did this in the next part of our journey. But the result, the answer to the question of positive, negative, or flat, is one of the most shocking discoveries in the history of science. The data tells us that our universe is flat. Not just kind of flat, astonishingly precisely flat. The error bars are tiny. The universe walks the razor's edge of critical density with a precision that defies coincidence. This flatness is a profound mystery. In a chaotic explosion like the Big Bang, you would expect the universe to be crumpled or warped. To end up perfectly flat is like balancing a pencil on its tip for 14 billion years. It suggests that something happened in the earliest fraction of a second to smooth out the cosmos, a rapid, violent stretching known as inflation. But let us not get ahead of ourselves. For now, we must internalize the three shapes. The sphere, finite, closed, destined to collapse. Parallel lines meet. The saddle, infinite, open, destined to freeze. Parallel lines diverge. The sheet, infinite, balanced, destined to coast. Parallel lines stay parallel. These are the three flavors of space. They are the topological destiny of everything that exists. And while we live in a universe that appears flat, the presence of localized mass, the stars and galaxies, creates pockets of curvature, little dimples and wells on that flat sheet. We are riders on a flat ocean that is rippled with waves. But how do we know this? How can mere humans, stuck on a rock orbiting an average star, possibly measure the curvature of a vast and visible void? The answer lies in the behavior of light. Light is the messenger. It is the cosmic surveyor. By watching how light behaves over billions of years, we can trace the shape of the terrain it has crossed. We can see the invisible curves. If the universe is a vast, invisible fabric, then light is the perfect thread to trace its shape. For us to measure the cosmic geometry, to determine if we live in a positive, negative, or flat universe, we cannot rely on terrestrial geometry. We need a ruler that stretches across billions of light years and a measuring tool that is beholden only to the universe's own structure. That tool is the light is the ultimate surveyor for two critical reasons. First, light travels along the geodesics of space-time. As established by Einstein, a geodesic is the shortest or straightest path between 2 points. In our everyday experience, the shortest path is a straight line. But in the universe, the shortest path is the one that curves, bends, and twists around every gravitational well created by mass and energy. Light does not care about the forces we feel. It only follows the topography of space-time. Second, light is ancient. The photons we use to map the curvature of the cosmos are not from our local solar neighborhood. They are light years old, billions of years old. They have journeyed across the entire observable universe, meaning they have sampled every curve, every bend, and every expansion of the fabric that has occurred since they were emitted. By studying how the path of light has been manipulated over cosmic time scales, we can infer the shape of the entire universe. The most intuitive way light reveals curvature is through a phenomenon called gravitational lensing. Imagine standing behind a thick pane of glass. If the glass is perfectly flat, the object you see on the other side looks normal. If the glass curves outward like the bottom of a wine glass, the object looks magnified or distorted. If the glass curves inward like the neck of an hourglass, the object looks. Massive objects in space, like galaxy clusters, act as giant cosmic lenses. They contain so much mass that they create deep valleys in the space-time fabric. When light from a very distant galaxy passes close to one of these clusters, the light is bent by the cluster's gravity, just as a lens bends light. If the alignment is perfect, the light from the background galaxy can be distorted into giant luminous arcs, or even multiple images of the same galaxy ringing the central cluster. The degree to which the light is bent, the severity of the distortion, tells astronomers two things. First, the amount of mass in the foreground cluster, even the unseen dark matter that constitutes most of its gravity. And second, the precise mathematical relationship between mass and curvature, confirming Einstein's geometry. Gravitational lensing is the physical manifestation of space being curved. We are not seeing a mirage, we are seeing space itself act as an optical element. But lensing shows us the local curvature caused by specific masses. To find the global curvature, the overall shape of the universe, we must use light to measure a triangle that is so immense it stretches from the early universe to the present day. This brings us back to the three geometric options: positive, negative, and flat. The distinction between them is measured by how light from a distant fixed-size object travels to us. Cosmologists search for a standard ruler, an object in the sky whose physical size is precisely known. If we know the actual size of the object, and we measure how large it appears to us in the sky, we can calculate the distance, and critically, the curvature of the space the light traveled through. This can be explained with the analogy of a flashlight beam. If the universe is flat, the light rays travel along parallel lines. The light from our standard ruler travels straight to us. The object's apparent size decreases perfectly with distance, exactly as predicted by Euclidean geometry. The geometry is a faithful, proportional map. If the universe is closed, positive curvature, the light rays, like the two parallel lines on the sphere, are slightly converging. They are bent toward each other by the density of the universe. This has the effect of acting like a magnifying lens. The object appears larger than it would in a flat universe at the same distance. The converging light bundles make the distant universe seem optically crowded. If the universe is open Negative curvature. The light rays, like the two diverging lines on the saddle, or slightly spreading out, they curve away from each other. This acts like a diminishing lens. The object appears smaller than it would in a flat universe at the same distance. The diverging light bundles make the distant universe appear vast and sparse. The critical challenge is finding a standard ruler that is reliable, ancient, and uniformly distributed across the cosmos. We cannot send a ship out with a yardstick, and we cannot assume that a galaxy today is the same size as a galaxy 10 billion years ago. The solution came from the light of the Big Bang itself, the cosmic microwave background. The CMB is the oldest light in the universe, dating back to when the universe was only about 380,000 years old. At that time, the universe was a uniform, hot fog of plasma. But within this fog, there were tiny ripples, fluctuations in density and temperature. These fluctuations are the seeds of all future structures. These ripples have a characteristic size that is governed by the speed of sound in the plasma and the age of the universe at the time. Crucially, the maximum size a ripple could grow before the light was released is an absolute physical constant. It is the standard ruler we need. Scientists look at the temperature map of the CMB. It is a modeled pattern of hot red and cold blue spots. The average physical size of the largest of these spots is the ruler. We know, based on physical laws, exactly how wide one of these spots should be in space. We then measure how wide it appears to us in the sky, measured in degrees of arc. This creates the cosmic triangle. The two long sides of the triangle are the light rays stretching from the spot of our telescope, and the short base is the physical size of the spot itself. By comparing the known physical size of the ruler to its observed angular size, astronomers can determine the geometric laws that govern the light's journey. The result of this measurement, conducted by satellites like WMAIM and Planck, was definitive. The spots appear exactly the size they should appear in a universe governed by Euclidean flat geometry. The light rays are neither converging nor diverging on a cosmic scale. The universe is, on average. This finding, one of the greatest triumphs of 20th century cosmology, meant that the total mass and energy density of the universe is precisely equal to the critical density. The critical density is a specific numerical value. It is the amount of mass and energy per cubic meter required to perfectly balance the outward momentum of the expansion with the inward pull of gravity. The fact that the universe is flat means that the density is not a little bit more, which would cause a big crunch, and not a little bit less, which would result in a big freeze. The universe is perfectly balanced, destined to expand forever, but at an ever-slowing rate that approaches zero. This simple act of measuring the spot size of ancient light provided the most powerful evidence for the global geometry of the cosmos. However, the fact that the universe is globally flat does not mean that locally it is rigid. The flat sheet of space-time is still wrinkled by every star and galaxy. The existence of black holes, of gravitational lensing, and of the gravity we feel on Earth all prove that space-time is locally curved. The universe is like a vast, stretched tablecloth. It is flat overall, but the silverware and the plates sitting on it create localized hills and valleys. Light, therefore, serves two roles. Locally, it bends around massive objects, confirming that mass creates curvature, general relativity. Globally, its overall path confirms that the average density of the universe is precisely balanced, making the overall geometry flat. Cosmology. This ability of light to carry both local and global information makes it the indispensable key to unlocking the true shape of reality. The light we observe is not a beam shot through a fixed grid. It is a path dictated by the geometry of the entire universe, a roadmap etched in the electromagnetic spectrum. It is the straight line that proves the universe is the ultimate paradox, perfectly flat, yet infinitely curved. We began by questioning the nature of space, moving from the illusion of emptiness to the reality of a flexible, curved fabric. We identified the three geometric possibilities: positive, negative, and flat, and discovered through the light of the ancient cosmos that our universe sits precisely on the razor's edge of flatness. This geometric conclusion is not an abstract fact to be filed away in a textbook. It is the definitive statement about the ultimate cosmic destiny. The geometry of the universe is the scorecard that dictates the final winner in the longest, most important struggle in existence, the war between the expansive energy of the Big Bang and the compressive force of gravity. Every cosmological model, every prediction about the far future of the universe, is a calculation based on this initial geometric condition. The curvature of space is the single most powerful predictor of the cosmos's timeline. If the universe had been discovered to possess positive curvature, the implications would be cyclical and finite. A closed universe is one where the total energy density, the mass of all galaxies, the energy of all photons, and the hidden mass of dark matter is greater than the critical density needed for force. The fate of a positively curved universe is a big crunch. In this scenario, gravity is the eventual victor. The initial momentum of the expansion, which has been driving the galaxies apart since the Big Bang, would be overwhelmed by the collective gravitational pull of the entire vast, self-contained system. The expansion would slow, hesitate for a moment, and then reverse. The universe would begin to contract. The light from distant galaxies would become blue-shifted as they rushed toward us, rather than red-shifted as they rush away. The cosmos would shrink, growing hotter and dense. Distances between galaxies would shorten, stars would begin to collide, and the fabric of space-time would compress. The end would be a final singularity, a return to a state of infinite density and heat, perhaps paving the way for a new Big Bang, initiating a cyclical model of birth, death, and rebirth. This geometric shape implies a finite lifespan and a violent, fiery ending. If the universe had been discovered to possess negative curvature, the destiny would be one of infinite desolation. An open universe is one where the total energy density is less than the critical density. The fate of a negatively curved universe is the Big Freeze. In this scenario, the expansion momentum of the Big Bang is too powerful for gravity to overcome. The universe would stretch and flare outward forever. The galaxies would rush away from one another at an ever-increasing pace, leading to immense cosmic isolation. Over trillions of years, the stars would burn out. The gas clouds would be dispersed too widely to form new stars, and the cosmos would become a vast, cold, dark wasteland dominated by black holes and cold, dead stellar remnants. The distances would grow so large that even the light from the nearest galaxy would take trillions of years to reach us, eventually dimming to invisibility. The final temperature of the universe would approach absolute zero. This geometric shape implies infinite size in a quiet entropic. The observed reality, confirmed by the precise measurement of the cosmic microwave background, is that our universe has zero curvature. It is flat. The fate of a flat universe is a perpetual yet decelerating. This flatness means the total density of the universe is exactly the critical density, balancing the scales between the Big Crunch and the Big Freeze. The expansion of the universe will continue forever, but etiquette will relentlessly slow it down. The rate of expansion will never reverse, but it will never truly stop. It will simply approach zero velocity over infinite time. This geometric flatness leads to a destiny similar to the Big Freeze, but less dramatically separate. The universe will still grow cold and dark, but the overall structure of space is the perfect Euclidean geometry we learned in school. However, the story of cosmic destiny became more complicated with the discovery of dark energy in the late 1990s. Dark energy is a mysterious, repulsive force that appears to be intrinsic to the fabric of space itself. It acts as a kind of negative pressure, driving and accelerating expansion. Because of dark energy, our flat universe is not just coasting, it is accelerating. The geometric prediction of flatness told us the universe would slow down forever, but dark energy is stunning cosmic accelerate. So while the geometry, the shape of the space, dictates a Big Freeze based on the mass-gravity balance, the contents, the dark energy, dictate an accelerating expansion. This acceleration leads to a slightly modified and arguably more desolate end: the eventual isolation of all galaxies outside our local group. The universe will still grow cold and dark, but faster than originally predicted. The fundamental point remains: geometry is destiny. The flatness of the universe is the most powerful constraint on all of cosmic evolution. It confirms that the total matter and energy budget of the universe is exquisitely balanced. This realization underscores the enormous scope of Einstein's revolution. The space we move through is not just a stage, it is the physical medium that holds the past, defines the present, and dictates the future. The simple equation for its geometry summarizes the entire 14 billion year narrative of the cosmos and all of its infinite future. By measuring the faint echoes of the Big Bang, we have managed to deduce the shape of the room we inhabit, and in doing so, have read the final chapter of cosmic history. The universe, vast and complex, is governed by a simple, elegant geometric rule. We live within a perfect, flat, but accelerating form, a cosmos of infinite extent, but finite energy density. We now transition from the theory of shape to the practical reality of measurement. We have identified the target. Now we must understand the tools. How precisely did we manage to measure the angle of a triangle that spans billions of light years? The answers lie in the faint, ancient clues the universe leaves behind, waiting for us to decipher. To determine the shape of the universe, we cannot look at the stars of today. We must look at the universe as an infant. We must become cosmic archaeologists, searching for a fossil imprint left over from a time before stars even existed. This fossil is the cosmic microwave background, or the CMB. The CMB is the single most important piece of evidence in cosmology. It is the echo of the Big Bang, the afterglow of creation itself. To understand how this faint glow reveals the universe's geometry, we must first understand the conditions of the early cosmos. Imagine the universe in its earliest moments, roughly 380,000 years after the Big Bang. At this time, the universe was not the cold, dark, structured place we know today. It was an environment of unimaginable heat and pressure, an ultra-hot, ultra-dense fog of plasma. This plasma consisted of nuclei, mostly hydrogen and helium, and a massive sea of free electrons, all mixed together with light particles or photons. The temperature of this environment was around 3,000 C, hotter than the surface of most stars today. In this fiery plasma, electrons were far too energetic to settle into orbit around the nuclei. Anytime a proton tried to capture an electron to form a neutral atom, a high-energy photon would instantly smash into it, knocking the electron free. This meant the universe was in a state of continuous ionization. Crucially, because the electrons were free, they acted as relentless scatterers of light. Photons could not travel freely. They were constantly colliding with the free electrons, scattering off them like billiard balls. Light was perpetually trapped in a blinding, dense fog. If you could have existed in this era, you would have been surrounded by an intense, brilliant white light, a state of perfect opacity. This is the epoch of recombination. As the universe expanded, it cooled. The expansion was the key to change. As the fabric of space stretched, the energy of the particles and the light within it was diluted. The temperature dropped steadily from 3. When the temperature dropped just below the critical threshold of about 3,000 Br, the entire dynamic of the universe changed in a cosmic instant. The photons no longer had enough energy to blast the electrons away from the nuclei. Suddenly, the protons and electrons were able to combine and form the first stable, electrically neutral atoms of hydrogen and helium. This event, 380,000 years after the Big Bang, is called recombination, or more accurately, decoupling. The moment the electrons were locked into the newly formed atoms, the universe changed from being opaque to being transparent. The free electrons that had acted as the ultimate light barriers were suddenly gone, locked safely away in atomic orbits. For the first time in cosmic history, light could travel unimpeded. The photons, which had been trapped and scattered for hundreds of thousands of years, were suddenly set free. They streamed out in every direction, filling the entire cosmos. This massive burst of light, released when the universe was 3,000 baht, what we detect today as the cosmic microwave background. Over the 14 billion years since, the universe has expanded by a factor of over 1,000. As the fabric of space has stretched, this initial burst of light has stretched with it. This stretching due to the expansion of space is what causes the light to redshift. The powerful, high-energy, visible light that was released at 3,000 does has been redshifted down the electromagnetic spectrum. Its wavelength has been stretched from the short, visible light range all the way down to the long, low-energy microwave range. The 3,000 does glow has cooled down to just 2.7. The CMB is not just an ancient light, it is a perfect snapshot of the universe. At 380,000 years old, it comes to us from every direction in the sky, a faint, uniform wash of microwave energy that permeates all of space. If you could tune a radio to this background static, you would be listening to the Big Bang. In fact, a small percentage of the static you see on an analog television screen is actual CMB photons hitting the antenna. But the real secret of the CMB lies not in its uniformity, but in its incredibly subtle variations. When first mapped precisely by the COBE satellite in the 1990s, and later by WMAP and the Planck satellite, scientists discovered that the CMB is not perfectly smooth. It has tiny, minuscule fluctuations in temperature. These fluctuations are incredibly small, about 1 part in 100,000. If the average temperature is 2.72 degrees Kelvin, the hottest spots are 2.72,001 degrees. These are the most important spots in all of cosmology. They are the slightly warmer and slightly cooler regions that correspond to the tiny density variations that existed in the plasma fog. The slightly denser regions, the cooler spots where gravity was pulling matter inward, would eventually grow over billions of years to become the first stars, the first galaxies, the first clusters, and ultimately the entire large-scale structure of the universe we see today. The CMB is the template for all structure. It is the architect's blueprint for the modern universe. And because the universe was uniform and isotropic at that time, these spots are perfectly distributed across the entire sky. This uniformity allows us to use them as our cosmic rule. The CMB is a sphere of light, a two-dimensional surface that completely surrounds us, and etched onto this sphere is the precise geometric information we need. The apparent size of those temperature fluctuations, the spots, is the key to measuring the curvature of space-time, and finally answering whether the universe is positive, negative, or flat. The profound history and precise nature of this relic light make it the perfect, unchanging, and global reference point for our measurements. The discovery of the minuscule temperature fluctuations in the cosmic microwave background by the COBE satellite was an enormous breakthrough, but it was the next generation of experiments, particularly the WMAP and the Planck satellite, that transformed those tiny spots into a precise geometric measurement. These satellites allowed us to perform the essential task of cosmic triangulation. We established that the entire question of cosmic geometry boils down to finding a standard ruler in the distant universe and measuring its apparent size. The CMB spots are that ruler. The physical size of the largest acoustic peaks, the largest characteristic spots in the CMB, is not arbitrary. It is a size dictated by physics that occurred during the brief 380,000-year epoch when the universe was an opaque plasma. Imagine the early universe was like a gigantic three-dimensional bowl of soup that was constantly being vibrated. In this soup, the slight overdensities of matter would try to collapse under gravity, while the intense pressure of the trapped photons would push back, trying to expand the spot. This created sound waves that oscillated through the plasma like ripples in a pond. These were not sound waves we could hear, but oscillations of pressure and density traveling at over half the speed of light. They were the universe's first sounds. The largest spots we see in the CMB are the regions that had enough time, exactly 380,000 years, to collapse under gravity and then rebound outward due to photon pressure, reaching their maximum size just as the universe became transparent. This maximum physical size, constrained by the speed of sound and the time elapsed, is known with incredible precision. It is approximately 1 million light-years in diameter. This 1 million light-year span is our standard ruler. Now we must measure the apparent angular size of this ruler. We look at the CMB map, find these characteristic spots, and measure how wide they look to us in the sky, expressed in degrees of. This creates our cosmic triangle, where the base of the triangle is the 1 million light-year spot, and the two long sides are the light rays that traveled for 14 billion years to reach Earth. The geometry of the universe determines how the light rays travel across that immense distance. If the universe were positively curved, closed, the fabric of space acts like a converging lens. The light rays would be bent inward, causing the 1 million light-year spot to appear larger than expected. If the largest spots appear to span 2 rows of arc or more, the universe would be closed and destined for a big crunch. If the universe were negatively curved, open, the fabric of space acts like a diverging lens. The light rays would be bent outward, causing the 1 million light-year spot to appear smaller than expected. If the largest spots appear to span less than half a degree of arc, the universe would be open and destined for a big freeze. If the universe were flat, zero curvature, the light rays travel along truly parallel lines over the cosmic distance. The spot would appear exactly the size predicted by standard Euclidean geometry for an object 1 million light-years across at a distance of 14 billion light-years. This angle is calculated to be almost exactly 1 degree of arc in the sky. The precision of the satellites was remarkable. They scanned the entire sky, measuring the distribution of hundreds of thousands of these spots, and then ran a complex mathematical analysis on the results, creating what is called the CMB power spectrum. The power spectrum is essentially a histogram that plots how many spots are found at each possible size. It is the signature of the early universe. The first highest peak in this graph corresponds to the size of that maximum rebounding spot, the 1 million light-year ruler. The result of the Planck satellite measurement, the most precise to date, was conclusive. The largest spots in the CMB have an angular size of almost exactly 1 degree. This single measurement is the most powerful evidence that the universe is flat. The total matter and energy density is so perfectly balanced that the space-time fabric has zero global curvature. The universe is critical. This finding carries enormous implications for the universe's total mass-energy budget. A flat universe requires the total density to equal the critical density. However, when we add up all the observable luminous matter, the stars, the gas, the dust, it accounts for only about 5% of that critical density. The fact that the CMB confirms flatness means the other 95% must be composed of the invisible components, dark matter and dark energy. The flat geometry is the constraint that allowed scientists to finally quantify the full, bizarre census of the universe. Ordinary matter, 5%, dark matter, 26%, dark energy, 69%. Without the CMB's precise geometric measurement, this cosmic census would be pure speculation. The temperature patterns on that ancient sphere of light are not just a historical curiosity, they are the definitive geometric proof that dictates the ultimate composition, and therefore the accelerating destiny of the entire cosmos. The CMB acts as the definitive compass and ruler for the universe at large, while the cosmic microwave background gives us the global average curvature of the universe by looking at its infancy. We need modern tools to confirm the large-scale, local structure, the actual physical way matter is distributed today. If the universe is geometrically flat, its contents should be distributed in a way that reflects that structure, yet still shows the curvature caused by local concentrations of mass. This requires us to literally map the heavens, creating a three-dimensional model of the universe's matter distribution. This is the purpose of modern, massive, deep space survey. By mapping the positions of millions of galaxies, we are mapping the intricate structure of the cosmic web, revealing how gravity has sculpted the matter within the flat space-time framework. Imagine taking a pin and sticking it into a colossal, dark expanse of foam. The foam is the fabric of space. The pin is a single galaxy. Now imagine doing this millions of times. The resulting pattern is not random. The galaxies are not scattered like dust on a floor. They are organized into a gigantic, interconnected architecture known as the cosmic web. The cosmic web is made up of three main features: filaments, long, thin strands of galaxies stretching for hundreds of millions of light years; voids, empty regions of space, where very few galaxies are found, often hundreds of millions of light years across; and clusters and superclusters, dense knots where the filaments intersect, containing thousands of galaxies pulled together by immense gravitational force. This web is the manifestation of the initial density fluctuations seen in the CMB. The slightly overdense spots in the ancient plasma became the nodes and filaments of the web, and the slightly underdense regions became the void. Gravity acted on those tiny seeds over 14 billion years, magnifying them into the enormous structure we see today. To map this structure, astronomers do not just need to know the galaxy's position on the sky, its two-dimensional coordinates. They need its distance, the third dimension. To measure distance, they use the galaxy's redshift. Redshift is the measurement of how much the light from a distant galaxy has been stretched, shifted toward the red end of the spectrum by the expansion of space during its journey. The greater the redshift, the faster the galaxy appears to be moving away, and the further away it is. By measuring the redshift for millions of galaxies, astronomers convert that velocity into distance, creating a three-dimensional map of matter. Surveys like the Sloan Digital Sky Survey, SDSS, and the current Dark Energy Spectroscopic Instrument DESA have successfully mapped millions of galaxies across enormous volumes of space. When we view these maps, two critical geometric features emerge that support the CMB's flatness conclusion and validate the local curvature of general relativity. First, the distribution of matter confirms the isotropy and homogeneity of the universe on the largest scales. Isotropy means the universe looks the same in all directions from our vantage point. Homogeneity means that if you take any sufficiently large cube of space, its contents, the density of matter, and the size of the structure look statistically the same as any other cube. This homogeneity is essential for a truly flat universe model. If matter were clumped unevenly on the largest scales, the geometry would be highly warped and chaotic. The uniform distribution of the cosmic web over distances greater than 300 million light-years confirms that the universe is smooth enough to possess a well-defined global flatness. Second, the mapping of the web allows us to measure the effect of gravity on a massive scale, confirming that local curvature is still at play. By observing how the light from background galaxies is distorted by the immense mass of superclusters, the knots in the web, we can use gravitational lensing to confirm the existence and distribution of dark matter. Dark matter, which constitutes 85% of the universe's mass, does not emit light, but it has gravity, and therefore it curves space-time. The visible matter, the galaxies, follows the curves created by the invisible dark matter halos. Mapping the cosmic web is essentially mapping the structure of these dark matter halos. The success of these deep space surveys lies in their ability to bridge the gap between the ancient geometric reality, the CMB, and the modern structural reality, the galaxies. The pattern of the cosmic web is the final result of the tiny ripples of the CMB, growing under the influence of gravity for 14 billion years. The galaxy distribution is the physical evidence that a globally flat universe is compatible with locally intense gravity. It shows us the mountains and valleys, the clusters and voids that sit atop the smooth, flat foundation of space-time. By confirming that the universe is both smooth and clumpy, smooth on the very largest scale, but clumpy on local scales, the galaxy maps provide the final visual evidence of the shape of the cosmos, a vast flat plane that has been wrinkled and sculpted by the relentless geometric power of gravity. To map the invisible structure of the universe and measure its geometric parameters, scientists rely on some of the most advanced technological instruments ever created. These tools are designed to overcome two enormous challenges: the extreme distance and the extreme faintness of the cosmic clues. No single instrument can map the universe's shape. Instead, A multi-pronged approach, using different wavelengths of light, is required to build the complete picture. The history of measuring cosmic geometry is defined by these specialized instruments, each built to capture a specific fragile piece of information. 1. Satellites for the cosmic microwave background. The global curvature. To measure the CMB, instruments must be placed in space, far above the Earth's atmosphere. The atmosphere emits microwaves and heat, which would completely contaminate the faint 2.7 Dickley signal coming from the Big Bang. COBE, Cosmic Background Explorer, launched in 1989. COBE was the first satellite to definitively prove the CMB's black body spectrum and to detect the minuscule temperature fluctuations. Its discovery of these initial ripples was the first step toward geometric measurement, proving that the early universe was not perfectly smooth. WMAP, Wilkinson Microwave Anisotropy Probe, launched in 2001. WMAP was the first to precisely map the CMB fluctuations with the resolution needed to measure the 1-degree spot size. It was WMAP that provided the first strong confirmation that the universe was within a few percent of being flat. Planck satellite, launched in 2009 by the European Space Agency. Planck provided the highest resolution, lowest noise map of the CMB ever achieved. Its measurements pinned the geometry down to a fraction of a percent of the critical density, confirming the flatness of the universe with staggering precision. The Planck data, or the gold standard for cosmic geometry. These satellites work by measuring the minute temperature differences across the whole sky, calculating the angular distribution of the spots, and translating that into the critical density parameter, which defines the universe's overall curvature. To map the modern structure of the universe, the cosmic web, astronomers use powerful optical telescopes on the ground, optimized for collecting light from faint distant galaxies. Sloan Digital Sky Survey, SDSS. This was a pivotal project that used a 2.5 telescope at the Apache Point Observatory. It created the first massive three-dimensional map of the cosmos, charting the positions and redshifts of over 3 million galaxies. The SDSS map vividly illustrated the filaments, clusters, and voids of the cosmic web, confirming that matter is distributed in a complex foam-like structure that emerged from the CMB seeds. DESI, Dark Energy Spectroscopic Instrument. Built on the legacy of SDSS, DESI uses a new instrument on the Mail telescope that can measure the redshifts of 5,000 galaxies simultaneously. Its goal is to create the largest 3D map of the universe ever, charting over 40 million galaxies. This level of detail is necessary to precisely map the subtle influences of dark energy on the expansion history, which is inextricably linked to the universe's These surveys do not measure curvature directly, but they map the distribution of mass. Since mass dictates curvature, the map of the galaxies is essentially a map of the universe's local gravitational valleys and hills. Telescopes in space are necessary to provide the sharp, high-resolution images required to measure the subtle distortions caused by gravitational lensing, the direct visual evidence of local curvature. Hubble Space Telescope. Hubble has been instrumental in capturing stunning images of distant galaxies being gravitationally lensed by foreground galaxy clusters. These images provide the visual proof that mass truly warps spacetime, confirming general relativity on cosmic scales. James Webb Space Telescope, JWST. JWST, with its superior infrared sensitivity, can see galaxies even further back in time than Hubble. It is being used to find and measure the faint, tiny distortions of light from the first galaxies which are lensed by the dark matter halos of intervening unseen structures. The combination of these tools, the satellites measuring the background geometry, the ground-based surveys mapping the three-dimensional mass distribution, and the space telescopes confirming the local curvature via lensing, creates a seamless, cohesive picture. The universe's shape is determined by its mass-energy density, which we measure using the CMB. The distribution of that mass is mapped by the redshift surveys, and the physical manifestation of that mass warping space is proven by gravitational lensing. All three lines of evidence converge on the same conclusion. The universe is a mathematically flat, geometrically critical structure that is nevertheless locally curved by the objects it contains. The final, essential step in understanding the universe's shape is the realization that the cosmos is not a silent, inscrutable entity. It is a source of immense data, leaving behind physical, measurable clues that define its form and composition. The convergence of multiple, independent lines of evidence is what gives the geometric conclusion its immense scientific power. The most profound clue is the CMB, but the universe also leaves its geometric fingerprint in several other critical observable datasets. Just as the CMB spots are a standard ruler in the early universe, a related phenomenon, baryon acoustic oscillations, BAO, provides a standard ruler in the modern matter-dominated universe. Baryon acoustic oscillations are essentially the frozen imprint of those sound waves that propagated through the early plasma. When the universe became transparent, the sound waves suddenly stopped. This left a distinct, measurable, preferred separation between matter that was bunched up, the center of a galaxy cluster, and the spherical shell of matter that was pushed out by the photon pressure. This preferred distance, which can be measured today across hundreds of millions of light years, is approximately 500. Because this distance is fixed by the physics of the early universe, it acts as a secondary, giant ruler in the modern galaxy map. When astronomers map the distribution of galaxies, they find that galaxies are not randomly placed. They have a very slight but measurable tendency to be separated by this 500 million light-year distance. By measuring this fixed distance against the observed redshift of the galaxies, astronomers can calculate the expansion rate and the geometry of the intervening space-time, providing an entirely independent confirmation of the CMB's conclusion. The universe is. The BAO signature confirms that space itself is not significantly warped over billions of light years. While not a direct measure of geometry, the observation of type Ia supernovae provided the most shocking clue about the universe's contents, which are inseparable from its shape. Type Ia supernovae are exploding white dwarf stars that serve as standard candles, objects whose intrinsic brightness is known. By comparing the known intrinsic brightness to the observed apparent brightness, astronomers can calculate the distance to the supernova with high accuracy. In the late 1990s, surveys of distant supernovae revealed that they were dimmer than predicted for a flat matter-only universe. This meant they were further away than they should be, implying that the expansion of the universe had been accelerating over the past few billion years. This was the discovery of dark energy. Dark energy is the mysterious component that constitutes nearly 70% of the universe's total energy budget. Its existence explains why the universe is simultaneously flat due to the high total energy density and accelerating due to its repulsive nature. Without dark energy, the matter density alone would suggest an open, negatively curved universe. But the supernova provided the clue that the universe has an immense invisible component of energy that keeps the total density precisely at the critical level required for perfect flatness. The geometry and the composition are thus unified by the supernova data. The final, often overlooked clue is the local curvature of time itself. Einstein taught us that gravity bends time. Near a massive object, time slows down. This effect, known as gravitational time dilation, is constantly being measured by our GPS satellites. GPS satellites orbit Earth at an altitude where they experience less gravity than receivers on the ground. This means the clocks on the satellites tick faster than the clocks on Earth by about 45 microseconds a day. If these relativistic effects, the curvature of space, and the dilation of time were not constantly calculated and corrected for, GPS systems would fail almost instantly. The fact that we must routinely and precisely account for the curvature of space-time in our daily technology is the ultimate physical proof that Einstein's geometric universe is not just theory. It is the fundamental structure of reality, holding true from the smallest clock to the largest galaxy. The universe has provided an abundance of clues to its form. The ancient spots in the CMB, the massive pattern of the BAO, the dimming light of exploding stars, and the precise ticking of our own clocks. All these distinct pieces of observable data weave together to paint a unified, powerful portrait of the cosmos, a universe that is geometrically flat, perfectly balanced, yet dynamically alive and constantly accelerating. These clues move the question of the universe's shape from a philosophical debate to a solved mathematical problem. But the question of whether a flat universe can still be finite, whether we can eventually loop back to where we started, is the last great geometric mystery that observational data must address. We have established the most stunning geometric fact about the cosmos. On the largest scales, the universe is overwhelmingly flat. This flatness is a statement about the average global curvature of space-time, confirmed by the ancient light of the cosmic microwave background. According to the mathematics of general relativity, a flat universe corresponds to an infinite volume. It should stretch out forever in every direction, boundless and endless. However, in the geometry of the universe, things are rarely so simple. The physical size of the cosmos, whether it is finite or infinite, is a question of topology, which is separate from, but related to, its curvature. Topology is the mathematical study of shapes that remain the same even when they are stretched, twisted, or distorted. A coffee mug and a donut, for example, share the same topology because each has exactly one hole. You could theoretically transform one into the other without tearing the surface. In cosmology, topology asks, how is the geometrically flat fabric of space connected? Imagine an ordinary two-dimensional sheet of paper. It is flat, and it is finite. It has edges. But now take that paper and join the left edge to the right edge, and the top edge to the bottom edge, like the surface of a classic video game. When an object leaves the right side, it instantly reappears on the left side. The resulting shape is a torus, the surface of a donut. This toroidal surface is still mathematically flat. If you draw a triangle on it, the angles still add up to exactly 180°. Parallel lines remain parallel forever. The geometry is flat, but the space is now finite and has no boundary. This is the great paradox of cosmic geometry. The observed flatness of the universe does not guarantee its infinity. It only guarantees that the geometry is Euclidean. The universe can be flat and finite, provided it has a non-trivial or multi-connected topology. A universe with a finite multi-connected topology is one where space loops back on itself. It has no edge, no wall you can crash into. Instead, if you travel far enough in a straight line, you would arrive back at your starting point. This idea fundamentally challenges our intuition about boundaries. We associate finite with edges. A swimming pool ends at the tiled wall, but the universe is not an object in space. It is space itself. Its boundary is defined by its connection. The surface of the Earth is finite, yet we travel across it without ever falling off an edge. In a similar way, a vast three-dimensional, flat space could be globally finite if its opposing sides are mathematically connected. The reason this is even a possibility lies in the initial conditions of the Big Bang. We only know the universe is flat on the scale of our current observations, which is the size of the observable universe, the sphere of space from which light has had time to reach us since the Big Bang. This observable sphere is about 93 billion light years in diameter. The actual total size of the universe, the part we can't yet see, might be much, much larger than our observable sphere, or it might be only slightly larger. If the universe is topologically finite, its size would be defined by the distance one would have to travel before looping back. For example, if the entire universe were 100 billion light years across, we would be traveling in a repeating loop. This concept changes the very meaning of distance and difference. If the universe is finite and loops around, then a distant galaxy we observe in the sky might not be a unique singular galaxy. It might be the light from our own Milky Way, having traveled all the way around the cosmos and arriving back at us billions of years later. In this case, we would be seeing an image of our galaxy as it looked in the ancient past, perhaps slightly distorted by the intervening gravity, but fundamentally the same structure. The question of whether the universe is finite or infinite is therefore transformed into a search for ghost images. Multiple appearances of the same ancient structure, separated by immense distances, corresponding to light that has circled the cosmos once, twice, or perhaps even many times. The observable flatness provided by the CMB tells us the universe has the right geometry for infinite extent. But the topological possibility allows for the geometric freedom to fold or wrap that space into a finite yet boundless structure. The universe's shape is both flat and potentially self-contained, a mind-bending combination that forces us to redefine what size and boundary mean on a cosmic scale. To grasp the implications of a multi-connected universe, we must explore how space could loop back on itself in 3 dimensions. This concept is not achieved by curving the space into a 4th dimension that would create a positively curved, closed universe, which we know is not the case. Instead, it is achieved through a set of boundary conditions applied to mathematically flat space. Imagine again the 2-dimensional torus we created by identifying and joining the opposite sides of a flat square. The geometric properties are preserved, but the path through the space is changed. In 3 spatial dimensions, a similar process creates a 3 torus. It is still Euclidean, but it has the strange property of repetition. If you traveled through the space, you would eventually encounter the same region of space again, approaching it from a different direction. The 3 torus is the simplest example of a multi-connected topology that is compatible with a flat universe. However, there are many other possible flat topologies, each one mathematically distinct and stranger than the last. These can be visualized by imagining a fundamental cell or block of space, which is then tiled throughout the cosmos. The 3 torus cubic cell, This is the simplest repeating block, where the universe is like a stack of three-dimensional cubes. If you leave one face, you enter the corresponding face of the next block, the quarter-turn space, the Horn space. This topology involves a twist. When you leave one side of the space, you reappear on the opposite side, but the universe is rotated by 90. Travel through this space 4 times, and you return to the starting orientation, the hemicube. Here, when you pass through one boundary, you emerge from the opposite boundary inverted or mirrored. Everything you see would be left-right reversed. All these shapes are examples of a flat geometry that is topologically finite. The total volume of the universe would be finite, equal to the size of that fundamental cell multiplied by the number of times it tiles the entire space. The consequence of a multi-connected universe is the phenomenon of cosmic repetition. If the light from a distant object has circled the universe, then we are not looking at a unique object. We are looking at a re-entrant path of light. If the looping distance were, say, 40 billion light-years, then every object beyond that distance would appear as a repetition of a structure that is topologically close to us. The search for this looping space is essentially a search for cosmic self-similarity on the grandest scale. The most direct way to search for this is by analyzing the cosmic microwave background. If the universe is finite and loops back on itself, then the ancient CMB sphere that surrounds us should contain repeating pattern. Imagine a finite universe that is slightly smaller than the observable universe. The CMB sphere, being the ultimate boundary of our sight, would be wrapped around the universe multiple times. When the light is released from the plasma, it travels outward, and some of it begins to wrap around the finite space. The light released from the plasma at 380,000 years would have been emitted at the same time in temperature from all parts of the finite space. Therefore, if the universe is finite, the CMB map should have pairs of circles that are mirror images of each other. Imagine 2 points on the CMB sphere. If they represent the same physical region of the early universe, seen from 2 different directions because the light has traveled around the loop, then the temperature patterns along the circles passing through those points should be identical. Astronomers have spent decades searching the Planck and WMAP data for these perfectly matched circles in the sky. Finding a specific set of matching circles would immediately reveal the size and the precise topology of the universe, whether it is a simple 3 torus or a more complex repeating shape. So far, no definitive, statistically robust matching circles have been found. This strongly suggests that if the universe is topologically finite, the looping distance must be larger than the radius of the observable universe, at least 46 point. If the looping distance is only slightly larger than our sphere of sight, the circles will be too small to detect with current instruments. If the universe is indeed much larger than the observable part, the question of finite versus infinite becomes less pressing for the immediate future. If the loop distance is hundreds of billions of light years, the universe is effectively infinite for any observation we can make. However, the geometric and conceptual possibility remains: a universe that is flat and infinite in its local geometry, yet finite in its global wrapping structure. The multi-connected space challenges our fundamental assumptions about the true volume of the cosmos. While the vast majority of current observational data points to a flat universe, the historic debate on cosmic shape focused heavily on the closed universe models, primarily because they offered a simple, compelling, and finite topology without invoking complex boundary conditions. These models, though largely discarded by modern CMB data, are essential for understanding the geometric possibilities and the power of the evidence we now possess. A closed universe is intrinsically finite. It is one where the total mass energy density is greater than the critical density, causing the space itself to have positive curvature. This curvature is the key. It allows the space to wrap around itself naturally without the need for artificial boundary identifications like the three torus. The geometry of the closed universe is that of a hypersphere or a three-sphere. Imagine the surface of a two-dimensional sphere. Again, you can walk forever without falling off, and you will return to your starting point. The 2D surface is finite and closed. The three-sphere is the same concept, but elevated to three spatial dimensions. If you traveled straight in a three-sphere universe, you would eventually loop around and return home. The universe would be finite. But since the curvature itself closes the space, it has no boundary. It is compact and self-contained. In the era before the CMB was mapped with high precision, the closed universe was often considered the most aesthetically pleasing model. It offered a cosmic cycle. The Big Bang leads to expansion. The curvature causes a return in the Big Crunch, and perhaps the crunch leads to a new Big Bang, a universe of infinite time, even if finite in space. The geometry of the closed universe also has specific rules. The angles of a triangle add up to more than an 80 do. Parallel lines always converge. We use these geometric rules to test the model. The CMB spot size measurement, which showed the angles were exactly 180 do, was the decisive blow against the simplest closed universe model. The precision of the Planck data strongly excludes a globally closed cosmos, at least one with a uniform, low-complexity topology. However, just as a flat universe can be topologically complex like a three torus, a closed universe can also have a complex topology. Instead of a simple three-sphere, it could be a dodecahedral space, where the universe is tiled by 12-sided fundamental cells. This was a particularly active area of research when the WMAP data initially suggested a slight positive curvature. A model called the Poincare dodecahedral space was proposed, which predicted a finite, positively curved universe with a characteristic repeating pattern in the CM. Though beautiful and mathematically elegant, the much higher resolution and precision of the Planck data ultimately ruled out the observable signature of this dodecahedral space. The key takeaway is the power of observational constraints. Geometry, as determined by the universe's density, dictates the large-scale curvature, density, critical density, a positive curvature, a closed. Density, critical density, zero curvature, flat. Density, critical density, negative curvature, a clopen. The robust measurement that the density is equal to the critical density, thanks to dark matter and dark energy, firmly places the universe in the flat category. This does not rule out the possibility of a complex topology in which a flat universe is finite, like the three torus, but it does rule out the simpler, closed geometries, like the three spheres. The geometry of our universe requires us to look beyond simple curvature and consider the complex connectivity of a flat space, which is far more subtle and challenging to test than the simple curved models. The most romantic and conceptually challenging implication of a topologically finite universe is the possibility of the ultimate journey, traveling far enough in a straight line to return to your starting point. This idea of a cyclical path is a direct consequence of a multi-connected, flat geometry, and it raises profound questions about our location and identity within the cosmos. If the universe were a finite three torus, the size of the fundamental repeating block defines the looping distance. Let's assume, for the sake of argument, that the looping distance is only 10 billion light years. If you began a journey from Earth and traveled in a straight line for 10 billion light years, you would eventually see the Earth reappear straight ahead. You would be approaching our solar system from the other side. You would see our planet, but as it was 10 billion years ago when the light left. This means that a finite universe requires us to redefine distant and ancient. Every object we see beyond the looping distance is an image, not a unique object. You might see the first generation of stars, the population 3 stars, not in the most distant corner of the cosmos, but in the relatively local region that is the light travel loop away. A galaxy 40 billion light years away might simply be the same galaxy that is only 30 billion light years away, but the light has circled the loop. However, for such an astounding prediction to be true, it must survive the test of the cosmic timeline. The age of the universe is about 13.8 billion years. The furthest light we can ever detect is the CMB, which was emitted about 30. This defines the radius of the observable universe at 46.5 billion light years. For us to have observed a full loop of light, the total size of the universe, the looping distance, must be smaller than the observable distance. In that scenario, the light would have had time to wrap around and reach us again. But since we have not found the telltale repeating circles in the CMB, and since the universe appears visually isotropic, it looks the same in all directions. The looping distance must be larger than our observable horizon. If the looping distance is greater than 46.5 billion light years, then for all intents and purposes, the universe is infinite to us. We will never have enough time to see the light from Earth loop back. And no matter how far we travel, we will never make it back to our starting point. The current age of the universe prevents the loop from completing its cycle within the bounds of our observation. Therefore, the geometric search for topological repetition is the final, ultimate attempt to place a definitive size limit on the cosmos. If future, more precise experiments do eventually find a faint signature of repeating circles in the CMB, it would be the most radical discovery in modern science. It would mean that the universe is flat, confirmed by the 1 degree spot. The universe is finite, confirmed by the repeating circles, and we live in a cosmic hall of mirrors, where what we see is a repetition of ourselves and our local cosmic neighborhood projected across immense distances. If, however, the search remains fruitless, the universe must be either truly infinite or simply so vast, its size far exceeding the limits of our observation, that the concept of returning to the starting point becomes a beautiful but unreachable geometric dream. The geometry of the universe is thus a dual constraint. The flatness dictates the Euclidean shape of the space, and the topology dictates its connectivity. Only the connectivity determines the ultimate size and whether the ultimate journey of cosmic return is physically possible. The discussion of cosmic geometry forces us to confront our most basic human intuitions about space, particularly the concepts of inside and outside. In our everyday lives, these concepts are absolute. We are inside a room. The room is outside the house. A boundary is a clear division between the two states. The universe, however, obliterates this distinction. When we consider the possibility of a finite universe, a closed hypersphere, or a flat, multi-connected torus, we must ask, what is it contained within? If the universe is finite, where is its edge, and what lies beyond it? The geometric answer is there is no outside. A finite universe, whether curved or topologically flat, is defined as a space with no boundaries. The mathematics of the geometry is complete and self-referential. In the case of a closed universe, positive curvature, the space curves into itself, much like the surface of a two-dimensional sphere curves into its own space. There is no outside to the surface of a sphere. The curvature itself closes the space. If you were to point a spaceship out, you would be pointing it into the geometry of the universe itself. In the case of a flat, finite universe, multi-connected topology, the space closes through identification. When you cross a boundary, you immediately reappear on the opposite side. There is no void beyond the boundary. The boundary is merely a geometric identification point. This idea that a system can be finite without having an edge is one of the most profound concepts in geometry and cosmology. It means that the universe is not an object that exists in a higher space. It is the higher space. This challenge to intuition extends to the notion of infinity. Our minds struggle with the idea of a truly infinite space, a space that goes on forever, without end, in which every potential arrangement of matter and energy must eventually repeat itself. If the universe is geometrically and topologically infinite, then it has no boundary and no loop. Any journey continues forever. In this scenario, the total volume of space-time is literally endless. The key to transcending our intuition is to embrace the geometric description. The concepts of inside and outside are products of our three-dimensional gravity-bound experience. The universe operates on a more fundamental topological level, where connectivity and curvature are the only defining limits. To live in a universe without an edge is to live in a reality where the fundamental nature of space is one of perpetual inclusion. There is no exterior. There is no ultimate vantage point from which to observe the whole. We are fundamentally and perpetually inside the most challenging distinction is the one we are left with, the difference between a universe that is truly infinite and one that is merely vastly larger than our ability to observe. If the loop distance of a topologically flat universe is 500 billion light-years, we will never see the loop close. To us, it is infinite. Yet, mathematically, it is finite. The physical ultimate size of the cosmos may forever remain an unanswerable question, lost in the shadows beyond our observable horizon. Ultimately, the shape of the universe is a challenge to our limited sensory perception. It demands that we think mathematically, not visually. The universe is a boundless geometric structure whose overall form governs the fate of time, motion, and every physical process within it. We do not merely observe the shape of the universe. Our existence is entirely defined by the geometric constraints of the space-time we inhabit. As we trace the vast architecture of the cosmos, a remarkable truth emerges. The universe is not merely something we observe, it is something we inhabit. Its shape governs the paths of galaxies, the flow of time, and the fate of everything that exists within it. Whether space is flat, gently curved, or folded back upon itself, its geometry quietly directs the universe's evolution. Expansion accelerates or slows, light bends. Distant galaxies drift beyond reach. All of this unfolds according to the shape of space itself. For humanity, understanding this shape is more than an abstract pursuit. It reshapes our sense of place. We are not standing at the center of a cosmic structure, nor at its edge, but embedded within a vast and subtle form that has been unfolding for billions of years. Much remains unknown. Our measurements grow ever more precise. Yet, the universe continues to resist simple description. Perhaps its true shape is more elegant and more mysterious than any model we can imagine. We do not merely observe the universe, we live within its shape. Good night.